There is a non-negative integer. There is a non-negative integer. There is a non-negative integer. D of A satisfying the following conditions. D of A satisfying following conditions. D of A is following conditions or properties, etc. Following properties or conditions. What is that? First one is D of A is less than D of A is less than D of AB. This second property, second condition. For any A comma belongs to. For any A comma B belongs to capital R. With B is not equal to 0. B is not equal to 0. There exist element Q and R. There exist elements Q and R. Elements Q. Q and R. Elements Q and R. In R such that ST means such that A equal to BQ plus R. This is nothing but basic formula, basic division algorithm. Do you know division algorithm? Dividend equal to divisor into quotient plus remainder. where R equal to 0. R D of R is less than D of B. Then D. The map D is called Euclidean map. The map. The map. D is called Euclidean map. D is called Euclidean map. R dimension function. Dimension function. The property 2 above is called Euclidean algorithm. Condition 2 is called Euclidean algorithm. Algorithm means what is algorithm? Step-by-step procedure is called algorithm. Euclidean algorithm. Example. Example. Every field is a Euclidean domain. Example. Every field is a Euclidean domain. Every field is a Euclidean domain. Let F be a field and define. Let F be a field create field, create field, and define d of a equal to 1. Define d of a equal to 1 for all. 0 is not equal to a, not equal to a. That belongs to a. Clearly, the condition 1 is above is satisfied. Clearly, condition 1 is satisfied. Satisfied. Condition 1 is satisfied. To prove second, to prove that second one, that a comma b belongs to a comma b belongs to f, and b is not equal to 0. B is not equal to 0. Then by taking, then by taking Q equal to B inverse A, Q equal to B inverse A, and R equal to 0, and R equal to 0. R means remainder. We have A equal to BQ plus R, BQ plus R. Then F is a equivalent domain. Then F is a Euclidean domain. Euclidean Euclidean domain. Then next definition. Next definition. Let us recall that a ring, let us, page number 220. Let us recall that a ring is called ring is called ring is called ring is called principal ideal ring. It's called ideal ring. Principal ideal ring is a principal ideal. Is a principal ideal. Principal ideal. Principal. An integral domain is called a integral is called a an integral domain is called a principal ideal domain. Ideal domain. Principal ideal domain. If ideal, every ideal in the integral domain is principal ideal. If every ideal in the very ideal in the ideal in integral domain is world domain. Integral domain is principal ideal is principal ideal. Principal ideal. For example, easy means example. The set Z of integers, set Z of integers the set Z of integers is a principal ideal domain. A principal principal ideal domain. Principal ideal domain. Since every ideal in Z, since every ideal in Z, every ideal in Z is principal ideal. Is principal ideal. Use this definition will prove one theorem. The theorem is important for 10 marks question. Theorem. 10 marks. Prove that every Euclidean domain. PT means prove that every Euclidean domain. Euclidean. L-I-T-E-N. Euclidean domain. Euclidean domain is a principal ideal domain. Is a principal ideal domain. Ideal domain. Proof. Proof of this thing. Proof of this thing. Let R be Euclidean domain. R be Euclidean domain. Domain. Euclidean domain. With the Euclidean map, with the Euclidean map, Euclidean map, Euclidean map. D. Euclidean map. Let F be an ideal of R. Let I be an ideal of R. I be an ideal of R. Means it of element. We shall prove that there exists small a belongs to I. We shall prove that there exists A belongs to I. So yes, A belongs to I. Such that, such that I equal to AR, that equal to AR, such that R belongs to capital R. And if I equal to, if I equal to 0, yes, then we take A equal to 0, we take A equal to 0, A equal to 0, so that I equal to AR. So that I equal to AR. So that I equal to AR. Suppose I is not equal to non-negative. Let I is not equal to 1. Then choose a non-element. Then choose a non-zero element. Then choose a non-zero element. Non-zero element. Then choose a non-zero element. A in I such that in I such that such that D of A, D of A is the least. D of A is the least. That is D of A. D of A. D of A less than or equal to D of T. Less than or equal to D of T. For all, 0 is not equal to B. That implies I. Implies I. We shall prove that I equal to A. We need to prove that. Prove that I equal to A. Since A belongs to I, since A belongs to I, since A belongs to I, and I is an ideal of R, it is an ideal of R, an ideal of R, ideal of R, ideal of R, ideal of R. We get that ER is subset of, we get AR subset of equal to I. Okay. To prove that I is subset of equal to AR, to prove that I is subset of equal to AR, yeah. Let us consider B belongs to I. Let us consider B belongs to I. B belongs to I. Then we can write Then we can write. Then we can write V equal to A cube plus R. V equal to A cube plus R. Where Q comma where Q comma R belongs to capital R. Q comma R belongs to capital R. And either R equal to 0. Either R equal to 0 or D of R is D of R is less than D of A. D of A. Since R equal to B minus A cube, B minus A cube, B minus A cube. And A comma B belongs to A comma B belongs to I. We have R belongs to R belongs to R belongs to. If R is not equal to 0, then dr equals less than dr less than d of A, which is a contradiction. The choice of A, which is a contradiction, is a contradiction. Choice of A. Is a contradiction. Choice of A. Choice of A. Therefore, R equal to 0. Therefore, R equal to 0. B equal to A cube. A cube. Which belongs to A. Okay. I is subset are equal to A R. I is subset are equal. And hence, A equal to A R. Equal to A R. Okay. So that I is a principal ideal. So that I is so I is principal ideal. Principal ideal. Principal ideal. Because R is a principal ideal domain. Thus, R is a principal ideal domain. Principal ideal domain. Ideal domain. Principal ideal domain. Not even principal. The converse of above result is not true. The every principal ideal domain is not a Euclidean domain. So, hence the theorem. This is the complete with the proof, hence proof. Next theorem, most important 10 marks question. Page number 221. Let R prove that. Prove that. Let R be Euclidean domain. Let R be a Euclidean domain. Domain. Euclidean domain. With Euclidean map D. Euclidean map D. Euclidean map D. Euclidean map D. Let A and B any non-zero elements in R. A and B any non-zero elements in R. Elements in R. Non-zero elements in R. Then the following hold. Following hold. A and B non-zero elements in R. Then following H. The following hold. Again, the first one. If B is not a unit, if B is not a unit, not a unit, then D of A, then D of A less than D of AB. Second, D of 1 less than D of A. Less than D of A. Third one, D of 1 equal to D of 1 equal to D of A. D of 1 equal to D of A. If and only if A is unit in R, if and only if A is unit in R, unit in R. The proof. 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 Suppose B is not in unit. Let B is not a unit. Unit. B is not a unit. B is not a unit. Put I equal to here. Put I equal to here. 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 Yeah, equal to I can put A equal to I. Yeah, yeah, that equal to AX plus that X belongs to R. Then 0 is not equal to A. 0 is not equal to A. 0 is not equal to A. It belongs to I. And D of A and D of A less than or equal to D of AX. D of AX. For all 0 is for all 0 is not equal to AX. 0 is not equal to AX, which belongs to I. Therefore, by above remark, I equal to, therefore, by above remark is page number 220. Above remark, for I equal to A, B, R. In particular, A belongs to I. In particular, A belongs to I. A belongs to I. That equal to A, B, R. And hence A equal to, hence A equal to ABX. ABX. For all X belongs to I. X belongs to X belongs to R. So the dx equal to 1. Bx equal to 1. And B is the unit. Is the unit. B is the unit. Which is contradiction to the hypothesis. Which is contradiction to the hypothesis. Is contradiction to the hypothesis. Then D of A is not equal to D of A. D of A is not equal to D of B. D of AB. D of AB. And hence and hence D of A less than D of AB. Less than D of AB. Second, By definition, by definition, by definition, by definition, d of 1, d of 1 less than d of 1 minus a, d of 1 into a, that equal to d of a. Pardon me, pardon me. Suppose that a is a unit in order. Unit a is unit in order. Unit in order. Unit in order. Suppose a is unit in order. Then there exists x belongs to, then there exists x belongs to 1, x belongs to 1, such that ax equal to I, and p of a is less than or equal to ax that equal to d of 1 less than or equal to d of 1 into a that equal to d of a, d of a. 223, 223, d of a. Hence, d of 1 equal to, hence, d of 1 equal to d of a, d of a. Conversely, conversely, suppose that conversely suppose that d of 1, d of 1 equal to d of a, d of by definition, by definition, by definition, by definition, there exists q and r in R. There exists q and r in R means set of numbers such that 1 equal to aq plus r, aq plus r, aq plus r. Where r equal to 0, where r equal to 0, r, d of r less than d of r, d of r less than D of 1 by 2 by it means by second condition above D of 1 D of 1 less than or equal to D of R D of 1 if R is not equal to 0 therefore R must be 0 therefore R must be 0 R must be 0 R must be 0 and 1 equal to A cube A cube. Therefore, thus A is the limit. Thus, A is the unit. A is the unit. Hence, prove. Two theorems we discussed it. Now, few definitions. Definition. Definition. If f of x equal to x equal to a naught plus a1x plus a2x square plus so on plus an x power n where an is not equal to 0 then n is called then n is called degree of f of x degree of f of x degree of f of x and it is denoted by and it is denoted by that is denoted by is denoted by degree deg of f of x. Example. F of x equal to 0 of x. If f of x equal to 0 of x, then f of x equal to 3x square plus 4x prime. 3x square plus 4x plus 3 is a polynomial of degree 2. Is a polynomial of degree 2. Degree 2. It is leading coefficient is its leading coefficient is leading coefficient is 3. Next definition. Polynomial whose degree is 0. Polynomial whose degree is 0, whose degree is 0, are called constant polynomial. Constant polynomial. Constant. Next. So, page number 223. Page number 223. Example sum 11.3.8. 11.3.8. Homework. 10 marks. Next. 11.3.11. Page 225. 25. Theorem. 11.3.11. Homework. Reverse. 10 marks. 10 marks. Page number 226. 226. Theorem. 11.3.12. 11.3.12. Homework. 20 marks. 20 marks. Possibilities there. 10 or 20 marks. The theorem. 10 or 20 marks. Next. 11.3.14. Page 227. 11.3.14. 115. 1.3.15. 10 marks. Next. Page number 229. Page number 229. Easy. This is general division. 11.3.17. Examples now. Homework for 10 marks. 10 minutes. Now, page number 230. Page number 230. 11 point exercise problem. Exercise problem. 11.4.2. And it's for 20 marks per 20. 20 marks. 20 marks. So, time is 10 minutes are there. We'll discuss one theorem. That is 11.4 reminder theorem. Next page. Theorem. theorem with remainder theorem. Remainder theorem. Remainder theorem. Remainder.
Sir, will this be for 20 marks?
Yes, this is for only 10 marks. Remainder theorem and factor theorem. So statement, page number 227. Because what they are doing exactly 8 o'clock, they are cutting our class. Yesterday, 2 times, 6:30 they cut it, and again 10 minutes before also, the host is progressing another program, another class is saying. I called up, that's why they didn't cut today. Let F be a field statement. Let F be a field. Let F be a field. F of x belongs to f of x belongs to L of x. And A belongs to small a belongs to F. Then f of a is the remainder. Then f of a is the remainder. Okay, is the remainder. When f of x is divided by, then f of x is divided by of x is divided by x minus a. Proof. Divided by x minus a. Let let g of x equal to x minus a. G of x equal to x minus a. G of x minus. Then by equivalent division algorithm, then equivalent division algorithm. In f of x. In f of x. We can write f of x equal to we can write f of x equal to g of x into q of x, q of x plus r of x. This is nothing but division algorithm. That is the dividend equal to divisor into quotient plus remainder. That equal to g of x means x minus a. No? That's substituting. G of x means x minus a into q of x plus r of x. Of x. Where q of x and r of x belongs to where q of x, comma, r of x belongs to f of x, means field of x. With r of x equal to 0, with r of x equal to 0, r of x equal to 0, degree of r of x is less than, degree of r of x is less than degree of x minus a. Yeah, x minus a. But degree of x minus a equal to 1. But here, degree of x minus a equal to 1. X minus a equal to 1. And degree of r of x. And degree of r of x less than 1. Then degree of r of x. Degree of r of x less than 1. Degree of r of x. Degree of r of x. Degree of r of x equal to 0. That is r of x is a constant polynomial. That is r of x is a constant polynomial. Constant polynomial. Constant polynomial in f of x. A by b. Let b, where b belongs to f field. So f of x equal to x minus a, x minus a, q of x plus b. Substitute a for x, we get substitute 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 a for x, a for x, a for x, a for x, we get f of a equal to a minus a plus b. That means that implies a minus a 0. f of a equal to b. F of a equal to b, which is a reminder then. Which is a reminder. Which is a reminder. Then. Is a reminder. Then. Which is a reminder. Then f of x is divided by x minus a. F of x is